Okay, so today we're going to talk about liquid and solid properties. Yesterday we talked about gas properties, and today we want to make sure we understand how gases are different than liquids, and then how liquids are different than solids, and essentially how each of these phases of matter has its own properties and why they have those properties. So you have some guided notes, obviously fill in the blanks as we go through here, and I'll kind of do some explaining along the way for each of the points that we bring up. So if you want to take any additional notes on the side or in the margins based on some things I say, that might be good as well. So let's talk about liquids. First of all, some properties of liquids. I have a fixed volume, and a liquid will usually take on the shape of its container. So unlike a gas, gases will fill up the entire container and take on the volume. Liquids are a bit more fixed, meaning the particles aren't moving around as much as they are in a gas. Particles do still, however, move. They are a liquid, they flow over each other, but not as much as a gas. There's more excitement, more energy in the particles of a gas than there are in a liquid. Now, let's think a little bit about the forces of attraction we've talked about. So we know inside of a certain substance we'll have, between the molecules, there'll be some attractive forces. There were dispersion forces, hydrogen bonding, and dipole to dipole forces of attraction. Now, in a liquid, we have forces of attraction present. Unlike a gas, gases did not have any of those attraction forces present. Liquids do, the part which causes the liquids to be more dense than a gas because the particles are attracting to each other. That's why we get more of a fixed volume. And it also allows us to still compress the liquid, but not as easily, just because we're more dense, so the particles are already closer together because they're attracted to one another. So these are some of the main properties of liquids you want to take note of. Okay. So let's take a look at two kind of properties or ideas associated with liquids. And one of those is called fluidity, which just means that liquids can flow. So the particles can kind of roll over each other and move around, things like that. So when I'm thinking about how easily something can flow, I have to think about the forces of attraction that are present. So first of all, I know in a liquid we have the particles are attracting to each other, which makes it more dense. But it depends on what kind of liquid I've got. So if I happen to have bromine liquid, for example, that is way more dense than water because the particles are bigger. Bromine is heavier than the elements that are involved in water, so the more attraction that you have, meaning if you're bigger, you're closer to the elements that you're next to, meaning you can attract more, then your flow goes down or your fluidity is less. So as the attraction forces go up, and that can be a result of size and mass, your ability to move and flow will be a little more restricted, so the flow rate will go down. Now, the other type of thing we have is called viscosity, and that's basically the measure of resistance to flow. So if something is flowing and I have it on a certain surface, or depending on what the liquid is, viscosity is just me measuring how easily it can flow, or what resistance there is to allowing the liquid to flow. Now again, this is directly related to attraction forces. So the more attraction forces you have in your liquid, it's going to slow down the ability for your liquid to move, which means there's more resistance to the flow, which means you have a higher viscosity. Now, things that can affect viscosity are shape, attraction forces, like we mentioned, and temperature. So attraction forces, the more you have, obviously the slower you can move because you're kind of stuck together more. The shape of the individual molecules has an effect on that. So for example, when we made slime in the Halloween lab, we made those polymers, and some people had a really thick slime based on their recipe, so it didn't flow around a lot. Other people had more of a flowy, watery slime based on the recipe. So when we did the slime recipe, we talked a little bit about, we had a hydrocarbon, we had kind of a long chain, and we called that a polymer. So shape is a lot of times related to polymers. We can think of basically long molecules or long chains of molecules. And the longer the chain and the bigger the molecule and the more awkward the shape, the more likely you are, the closer you are to other elements because you're bigger, and that basically means you can attract more, and if you attract more, then you move slower because you're stuck together more. So the bigger you are will also affect, and your shape will affect how you can flow, or that resistance, the amount of resistance there. Now, if I have temperature, if I heat up a liquid, for example, heat is a form of energy, so the more energy I pump into the liquid, which is in the form of temperature, the more excited the particles become, and the more excited the particles become, the more that they're moving around, so the less they're attracted to each other. So the less attraction forces you have, the easier it is for you to move. So here are the relationships we want to make sure we remember for viscosity. So if I have more attraction, then I have more resistance, so to my ability to flow, which means the viscosity goes up, the resistance goes up. If I increase temperature, then viscosity will go down, meaning I've pumped in more energy, particles are more separated and less attracted, so then the viscosity or resistance goes down. Okay, so these three relationships you'll want to remember. So here I have attraction versus flow, and if you remember direct versus indirect relationships, this will be indirect because as one thing goes up, the other goes down. Same thing with temperature and viscosity. This is also indirect. But attraction and viscosity is direct because both things are either increasing or decreasing. Now, when I think about viscosity and kind of fluidity, you can think of, I have a picture here, a cup of water, and if you put in food coloring, the liquids have the ability to flow. So I don't even really have to mix this. The liquids will kind of flow past each other, and based on the attraction forces, that may be quicker or slower, and eventually the food coloring will disperse throughout the liquid, just based on the fact that liquids will move past each other, they're fluid, and they can flow. So I'll give you, make sure you got everything written in, I'll give you a few seconds to do that. Okay, the other two properties of kind of associated or ideas associated with liquids are what are called surface tension and capillary action. Surface tension, the formal definition here is just the energy required to increase the surface area of a liquid. And this definition, I know, is a little bit hard to understand. We're going to kind of look at it with respect to attraction forces. So we always want to link up some of these properties we're talking about today to how attracted are the pieces and forces within a molecule or within a substance, and that'll affect kind of the properties we see in liquids. So one way we can think about surface tension, and you've probably experienced this, is when you see insects and they appear to kind of walk on water. This is because in water, we know water is H2O, and water will have hydrogen bonding going on inside of it, and hydrogen bonds were our strongest forces of attraction. So when insects walk on water, they're taking advantage of all of those strong hydrogen bonds. Now, within a certain substance or certain liquid, the particles or the forces between the particles that are present, those can pull in any direction. They can be attracted to molecules above them, below them, to the sides, doesn't matter. So when I increase surface tension, it basically means the molecules that are kind of maybe attracting in a downward direction actually move to the top part of the liquid. And when they move to the top, For example, in the case of water, if I have molecules moving kind of to the top and attracting to the things above them, then I'm increasing all of the bonds at the top of the liquid, and I'm increasing the forces of attraction, meaning the top of the liquid is a little stronger, and I get what's called surface tension. So when you experience surface tension, you can see like insects walking on water, they don't break through. They're kind of taking advantage of, they're light enough to take advantage of walking basically on all of those hydrogen bonds, which are super strong. So the stronger attractions you have in your liquid, the stronger the surface tension can be. So in the case of water, we have hydrogen bonding. Certain other liquids, there's like dipole to dipole. Certain other polar liquids, we have dipole to dipole attractions, which are fairly strong. But then liquids with obviously dispersion forces of attraction wouldn't be as strong, and we wouldn't get as much surface tension because there's not as much attraction. Now, here's, like I said, we have an example of water. We know that has a high surface area, which means I have a lot of hydrogen bonds, and they're attracted kind of to the top of the liquid. So when they hang out around the top, that means I have all that strong attraction stuff, and I can't break through it. Now, soap, when you're washing the dishes, things like that, soap will break down the bonds kind of between, it'll weaken those hydrogen bonds, and it will then decrease the surface tension. And if you have something that decreases surface tension, that's called a surfactant. So soap would be an example of a surfactant. It's breaking down bonds and weakening the ability to have a strong surface tension. So here's a picture, obviously, of a bug, some sort of mosquito thing, I'm not really sure. But anyway, this is walking on water. So here you can kind of see the tension at the surface. So the insect doesn't really sink through. It's literally kind of walking on those bonds. And the more of those bonds that hang out on the top, the less likely this insect is to fall through. So here's kind of how you can think about it. Instead of, having more of a downward pull inside of the liquid, if we can get more of a pull at the top, so if we're pulling out and hanging out around the top, we'll have more surface tension. Another property of water is capillary action, and here's the definition of that. We have attractive forces that attract molecules in a liquid. So if water's in like a glass tube, or like when we measure water in the lab in a graduated cylinder, the water we know forms what's called a meniscus, and that's basically because there's attractive forces between the glass and the water particles, and it kind of draws the water up the side. Okay, the skinnier your tube, the more this will be curved. The more your meniscus will be curved. This type of curving down is called a concave meniscus, and mercury goes against that. Mercury actually kind of repels away from the glass, so it will bubble up like this, which is called a convex meniscus. So concave, it's going down in, and convex, it's going up. Now capillary action, again, that's just the fact that the water is attracting to the glass, so it's giving it kind of a different shape. If you put a paper towel on a liquid and you want to soak it up, capillary action is what's causing you to soak up that liquid. So if I have paper towel and I put it in a water spill, then the water molecules are attracted to the cellulose fibers, basically the paper, in the paper towel, and they creep up the paper towel based on the attraction forces that are there. So I'm going to stop this video here. So we'll play the next video, which has a few properties of solids. There's less of those than there are liquids, but we'll run out of time and it'll pause in an awkward spot. So go ahead and start up the other clip. We'll finish up the notes and then we'll go from there.